Welcome to this explainer. Today we're diving into what is essentially one of the wildest detective stories in all of astrophysics, figuring out the properties of cosmic objects that literally trap light itself. We're going to explore a completely fascinating, incredibly elusive characteristic of the universe's most extreme phenomenon. We're talking about black hole spin.
Just think about it for a second. How exactly do you measure the rotation of an object you can't even see? Imagine trying to measure the exact spin of a toy top in a pitch-black room that happens to be millions of light years away. That is the seemingly impossible challenge we're tackling today. By their very definition, black holes emit no light, but their rotation fundamentally dictates the structure of entire galaxies, and it powers some of the most violent energetic outflows we've ever seen. So how do we know they're spinning, and how fast are they actually going?
Let's start with the ultimate cosmic mystery, identifying our main suspect. According to the no-hair theorem in general relativity, black holes are shockingly simple. Think about stars or planets for a moment. They've got mountains, varying magnetic fields, completely different chemical compositions, right? But once a star collapses into a black hole, all those distinguishing features, all that hair, just vanishes. An astrophysical black hole is defined almost entirely by just two things, its mass and its angular momentum, which we call spin. Technically, electric charge is a third parameter, but out in the astrophysical universe, it's completely negligible. So really, mass and spin are the only surviving DNA of a black hole.
When astrophysicists talk about this rotation, they use a dimensionless number called the spin parameter, or A star. It scales from exactly 0 for a completely static, non-rotating Schwarzschild black hole all the way up to 1. A spin of 1 represents a maximally spinning Kerr black hole that is literally pushing the absolute speed limits of the universe. And the sign of this parameter? That just tells us if the surrounding disk is rotating in the same direction as the black hole, which is prograde, or in the opposite direction, which is retrograde.
So that's the suspect. Now let's look at space-time in a whirlpool, the scene of the crime.
Because the spinning black hole doesn't just sit there quietly. It actively weaponizes the space around it through a mind-bending phenomenon known as frame dragging. Since gravity in general relativity is the actual curvature of spacetime, a rotating mass physically drags the very fabric of spacetime along with it. It acts exactly like a cosmic whirlpool. If you were floating near a spinning black hole, you'd be swept up in this rotational current. Even if you fired your spaceship's engines with maximum thrust just to stand still, you couldn't do it. You simply cannot fight the current of gravity.
This dragging effect creates a totally bizarre pumpkin-shaped region right outside the actual event horizon called the ergosphere. It is bounded by what's called the static limit. Inside this ergosphere, the frame dragging is so utterly extreme that absolutely nothing, not even light itself, can stand still relative to the rest of the universe. You are physically forced to rotate with the black hole.
So how does spin physically change the neighborhood? Well, take a look at the innermost stable circular orbit, or the ISO. This is the absolute closest a particle can orbit before it just plunges right in. For a static, non-spinning black hole, this stable orbit is at a radius of 6. But if you have a highly spinning prograde black hole, it dramatically shrinks that safe orbit down to a radius of just 1. To put that crazy scale into perspective, if our own galaxy's supermassive black hole, Sagittarius A star, is maximally spinning, matter at its inner edge orbits the whole thing in just 2.7 minutes. If it were static, that same trip would take nearly 20 minutes.
Let's move on to illuminating the invisible. What are our interrogation tools?
Since the black hole is pitch black, we have to interrogate the accretion disk swirling around it to somehow see this spin. The detective work here is incredibly sophisticated. Astronomers mostly rely on two leading methods. First, there's X-ray reflection spectroscopy. Basically, X-rays from a hot corona bounce off the inner accretion disk and interact with iron atoms. Because that disk is whipping around at a fraction of the speed of light deep in a massive gravity well, the iron emission lines get totally smeared and distorted. The exact degree of that smearing tells us how close the disk is to the event horizon, which, as we just learned, reveals the spin. The second tool is the continuum fitting method. Rather than looking at specific elements, it analyzes the raw, overall heat and brightness at that innermost orbit to back-calculate the spin.
But now, beyond X-rays, we have the Event Horizon Telescope. This incredible globe-spanning network can actually trace spin by looking at the ultra-fine details in the direct images of supermassive black holes. They're looking for sub-images within the photon ring, these S-shaped streams of infalling plasma that literally have to turn around because of the ergosphere. They can even observe the flipping signs of linear polarization caused directly by frame dragging.
Which brings us to spin-driven outflows and the Blandford's Nyack process.
Because look, spin isn't just a passive property to be measured for some catalog. It's a colossal energy reservoir powering some of the most spectacular phenomena in the entire universe. Here's how this engine works step by step. Step 1. Extremely strong magnetic fields from the accretion disk thread directly through the event horizon. Step 2. The frame dragging inside that ergosphere literally twists those magnetic field lines into a tight helix. Step 3. This massive differential rotation generates unscreened electric fields that create huge cascades of electron-positron pairs. And finally, Step 4. This extreme environment violently launches a highly collimated, relativistic jet of plasma straight out into deep space. The black hole acts as an unfathomably powerful electromagnetic dynamo, powered entirely by its own spin.
Now let's look at the ripples of ringing space-time, the purely gravitational clue.
We are actually entering an era where we can detect spin using a completely different set of clues. We don't even need light anymore. We can just use gravitational waves. When two black holes collide, they violently ripple the fabric of space-time. Right after that chaotic merger, the newly formed single black hole goes through a phase called ringdown. Think of it like a struck bell vibrating with specific frequencies that tell you its shape and size. While the ringing spacetime of a new black hole emits these damped sinusoidal signals, and those quasi-normal modes cleanly and directly encode the black hole's final mass and, you guessed it, its spin.
To show you just how precise this new science is getting, consider the incredible GW250114 merger. This event was the absolute loudest gravitational wave detection to date. It boasted an immense network signal-to-noise ratio of 80. In astrophysics, that basically means the signal was incredibly loud and crystal clear, which allowed physicists to probe the invisible structure of black holes like literally never before.
By isolating the complex, nonlinear ripples in this ringing space-time, researchers proved that these relativistic waves actually interact with each other. The data gave them a statistical certainty, a Bayes factor of 74, which essentially rules out any chance of a false alarm. So we're no longer just guessing. We are directly hearing the nonlinear dynamics of gravity, confirming the exact spin of the black hole.
Finally, let's wrap this up with the cosmic fossil record, the motive.
So why does measuring this invisible property actually matter so much? Why do astrophysicists spend their entire careers trying to pin down this one-dimensionless number? Well, as this brilliant quote points out, spin acts as a cosmic fossil record. A stellar mass black hole born from the sudden collapse of a massive star is going to have a spin that reflects the core dynamics of that specific dying star. But on the flip side, supermassive giants at the centers of galaxies grow over eons. A black hole that grew from random clumps of gas falling in from all different directions, that's going to have a really low spin. But one that grew from prolonged, steady accretion from a massive disk or from huge galaxy mergers will be spun up to absolute extreme velocities. The spin literally tells us the life story of the black hole.
To summarize everything we've covered in this explainer, spin really is the key to unlocking the universe's most extreme physics. It reveals exactly how a black hole was born and grew. It dictates how efficiently infalling matter gets converted into blinding light. It acts as the engine driving massive relativistic jets that can physically shape the evolution of entire host galaxies. And maybe most importantly, measuring spin gives us our absolute best, most pristine laboratory for testing the limits of Einstein's general relativity.
We've unpacked a lot today about the profound mystery of black hole spin. We've seen how frame dragging, glowing accretion disks, and the ringing of space-time itself allow us to measure the truly unseeable. But knowing just how deeply these whirling giants govern the structure and evolution of our universe, well, it leaves us with a lingering thought. If the invisible, spinning hearts of darkness shape the very galaxies we live in, what other cosmic secrets are they dragging into the light? Thanks so much for joining me on this explainer, and keep your eyes on the stars.